Hey guys, today's video is going to focus on just a quick review of how to write out acid-base reactions. Okay, so the first thing I want to take a look at is when we have an acid, basically just be dissolved in water. How does it interact with water? And so first, let's take a look at a case where we have a strong acid, and hydrochloric acid, kind of react with our water molecule here. You'll notice that there's a reaction arrow as opposed to an equilibrium arrow because this is a strong acid. So we're assuming 100% dissociation and 100% protonation by the water molecule to become hydronium. So this is maybe how we'd represent this. That being said, given 100% dissociation or near 100% dissociation for the HCl there, if I was working towards, say, a net ionic equation, I might write out my H plus my Cl minus. I break that up. I would not break up the molecular water. My hydronium ion's good to go. Chloride, good to go. So if I wanted to come up with the net ionic, I can cancel out the chloride ions on both sides. And what we find is that we essentially just have the free proton, encountering our liquid water molecule there to become the hydronium ion or the protonated form of water. Okay, so this would be the net ionic that is symbolic of the following process. Let's say I had nitrous acid and I were to see how that engages with the water molecule. We know this is an equilibrium arrow that should be used because nitrous as opposed to nitric acid is a weak acid. Therefore, we won't have 100% dissociation. So when I go to come up with my net ionic equation, I'm not going to break this up because, again, it's a weak acid. We consider it almost to be molecular. It's not composed of component ions. Water is good to go. And then again, I cannot cancel out either of my ions because I do not see them on the reactant side of things. So this would be the net ionic. Let's say I wanted to talk about the acid ionization constant, right? So my Ka value for the second, that bottom kind of weak acid reaction there. Products over reactants, here are my products. So I have my H3O plus, which is synonymous. Hydronium is synonymous with the free proton H plus there. I have the nitrite ion concentration there, all over the concentration of my my reactant nitrous acid, I should say. Okay, so this is what my Ka value would look like for that bottom process there, which again, we're getting into acids and bases, but I think that falls under the realm of equilibrium for sure, so probably fair game on our upcoming exam. Okay, let's say I want to talk about bases and water. Go on to the next section here. Let's say I was dealing with something that was hydroxide based, for lack of a better term. If I have solid sodium hydroxide and I dissolve that in water, when we go to talk about the basicity that is accomplished, we really just write this as a dissociation equation, where it's this free hydroxide that is constituting why it is acting as a base. I can't cancel anything out given that these are kind of both in the solid state. We know that our sodium hydroxide is a strong base, again, tending towards that 100% dissociation, hence why we've used a reaction arrow. Whereas with magnesium hydroxide, given the small size of magnesium and the fact that it carries a +2 charge, we have pretty strong Coulombic attractive force between that cation and both anions there, which makes it a little bit less soluble in water. It's a little bit harder to separate those two ions by the polar water molecule. So we've represented this with an equilibrium arrow because, again, it's not 100% dissociating into the magnesium, the two equivalents of the hydroxide there. In a final case, let's see what happens. And we just got done kind of reviewing this in our organic review. Let's say we have methylamine. And again, we have this aqueous form. It's interacting with our liquid water molecule here. What happens is there's going to be a lone pair on that nitrogen that has the ability to accept a proton, right? So in that way, it's a Bronsted-Lowry base. As it accepts that proton, it becomes NH3 plus here, right? We're going to end up getting a positive formal charge on the nitrogen. Doing so, it deprotonates the water molecule. And again, we get that hydroxide there, which is really how we should consider this to be a base, right? It'd be this concentration we'd be measuring, demonstrative of, say, a POH and therefore pH. As far as a Kb value, so our base ionization constant, for this third equation here, we're talking about that concentration of hydroxide multiplied by the product, multiplied by the concentration of the methyl ammonium at this point, and then over the concentration of just methylamine reactant. Okay, so again, we've taken a look at how acids can engage with water, how bases can engage with water. What I want to do now is just work through 3 quick examples of how we can talk about, again, the similar process, either how acids and bases act as they encounter water molecules, or perhaps acid-base reactions themselves. So the goal would be for these questions is to write out the net ionic equations. So we have sodium hypochlorite dissolving in water for our first example. Let's get sodium hypochlorite down on the page, plus our liquid water molecule, okay? Now, given that this is sodium, again, sodium, potassium nitrate, ammonium, these things are going to be always soluble with whatever other ion they're with. So I'm going to break this up straight away into its component ions, the sodium and the hypochlorite, ClO minus here. Okay. Now water obviously cannot break down. Okay. What I want to do is I want to figure out, well, what is the reaction that's actually going to take place? Okay. What we should key in on is the fact that the ClO minus, that is the conjugate base of the weak acid HClO, or hypochlorous acid, right? So hypochlorous acid is a weak acid. This is the conjugate base. And so what this hypochlorite ion is going to do is that it is going to deprotonate our water molecule. And doing so, we'll still have our sodium kind of chilling. This ClO minus is going to actually pick up a hydrogen. So we'll say HClO. And then we have our deprotonated form of water, which at this point is just hydroxide. Okay. So what we find is, working towards that net ionic, is that we can cancel out sodium on both sides, and we are left with the hypochlorite ion, aqueous, plus a water molecule. Right, we're not going to break up molecular water, in equilibrium with the HClO here, the hypochlorous acid. Again, that'll be aqueous, and then plus our aqueous hydroxide here. Okay, so literally what we're doing is, by adding in this salt that contains a conjugate base, we are going to be creating a basic solution there. In the second example, acetic acid, lithium hydroxide, again, just kind of reinforce what we saw with organic. No doubt you'd be given the formula of acetic acid, but it's HC3COOH, okay, aqueous. Lithium hydroxide, let's just straight away, in the interest of time, break that up into component ions. So lithium plus our